Hey everybody, it's Dr. J, and today we're talking about standard enthalpies of formation. Let's talk chemistry. So we've been talking about enthalpy, and a couple ways to figure out your enthalpy is using calorimetry or Hess's law. So remember, calorimetry is just basically, doing different experiments to find your enthalpy. Hess's law is where we add up our equations. Check out the previous videos for those two. Today we're talking about standard enthalpies of formation, and this is actually the most convenient way to find your enthalpy. So with this standard, there's three parts. The first part we're going to talk about is standard state. So standard state is defined with a set of conditions. So if you got a gas, you're going to be at 1 atmosphere pressure. If you have a pure solid or liquid, it's going to be mostly stable at 1 atmosphere pressure, and the temperature is usually going to be 25 degrees Celsius. Where if you're in a solution, your concentration is going to be 1 molar. All right, so these are the standard states of these particular, states of matter. Okay, so it must meet those conditions as well. The standard enthalpy of change, right? The enthalpy of change when all reactants and products are in their standard states. So they got to be in their standard states to even have this occur. Okay, the standard enthalpies of formation. And then lastly, with standard enthalpy of formation, the enthalpy of change for the reaction forming 1 mole of a pure compound from its elements. Basically, to sum this up, per elements in a standard state will be 0. Okay. And we're actually going to look at this in a little bit to explain this a little further. So, what equation are we using, Dr. J? Well, we're going to use this equation down here to find your standard enthalpies of formation. This is why it's so convenient. You're essentially going to do the sum of all your products minus the sum of all your reactants. That's it. Okay. So we're not adding up any equations, flipping them around, changing signs. We don't got to do any experiments, right? We're literally just going to use the sum of our enthalpy or formations from our products minus the sum of our enthalpies or formations from our reactants. Okay. And this n here is going to be based on a coefficient in the actual reaction. A great thing about standard enthalpies of formation is that the standards are already defined for us, right? As I mentioned before, the chemists from a long time ago, they did all this for us. That's to sum it up real quickly, everybody. They did it for us. We got the information so we could use the information. Let's talk about quickly what I was talking about with zeros. Notice all elements are just going to be 0. So if it's an element, in this case, 0, 0, BR2 is going to be a 0. So just pay attention to that when you do these type of problems. So let's actually calculate the standard enthalpy change. So I'm going to show you guys the two different ways, right? I'm going to show you the Hesss Law way, and then I'm also going to show you the standard enthalpies of formation way. Okay, so this is a reminder if you guys didn't check out the Hesss Law video. So with Hess's law, we know that we're adding up our equations, right? So in this case, we need to figure out our final equation. CH4 plus 2O2 gives me CO2 and H2O. This is what we're trying to figure out. What is the enthalpy of change for this particular reaction? Hess's law, we have a series of reactions that we can add together to get this equation here. So in this case, if I'm using Hess's law, they give me my three equations, right? We got graphite, H2O gives me CH4, and then we got our enthalpy right here. Carbon, oxygen here gives me CO2, and then we got our enthalpy here, and then we got our last equation, hydrogen plus oxygen gives me water. We got our enthalpy here. So how are we going to add these up to get my enthalpy of change? So the first thing I'm going to do here is I'm going to reverse my first reaction. Now, why am I reversing my first reaction, Dr. J? Uh, I'm reversing it is because this is the only reaction with CH4. So CH4 has to be a reactant, not a product. And right now in this equation, it has it as a product. So let's reverse it, put it as a reactant now. My reactants become products here, and my enthalpy goes from a negative 74 to a positive 74.6 kilojoules. All right, so that's the first thing I did. Second thing I'm going to do here is now, right, just bring down my second equation. So once I bring down my second equation, what we're going to see here is that my graphite, what's going to happen? They're going to cancel out because I have this now as a product because I reversed them. And if I bring this down, my carbon still stays on my reactant side, so that cancels out. That's gone now. Okay. Now let's look at my third one. In my third equation, what did I do here? Well, I kept it the same. I didn't reverse it, but I did multiply it by 2. Now, the reason why I multiply it by 2, right, is because I have 2 hydrogens here in my very first reaction. So notice, y'all, I had it already crossed out because I want y'all just to remember. These are the only things we want in our final equation. Do we see hydrogen? No. So we need to understand we got to cancel this hydrogen out eventually. And it's able to be canceled out by using my third equation here. So I multiply it by 2. Now I got 2H2. But not only do I have 2H2, remember, your oxygen will be multiplied by 2. So now I got 1 oxygen. My waters are multiplied by 2. So now I got 2 waters. And as well, my enthalpy will be multiplied by 2. So now I got negative 483.6 kilojoules. Okay. So my hydrogens are gone here, cancel out. Carbons are gone, cancel out. Now, what I have left is I see I got CH4, cool, and then it's a reactant. Okay, so it's matching up there. I got an oxygen here, cool, and I can see that it's going to be a reactant, so it's matching up there. I also have another oxygen as well. So if I add both my oxygens together, I'm going to notice that's 1, 2. That's 1, 2. CO2 needs to be a product, and it is a product in my second reaction. Cool. And let's look at my waters, right? In this case, I got my water. And they are as well going to be in my products. So if I add up everything that I see here, we're going to get our final reaction plus our enthalpies. And just to let everybody know, forgot to add my 2 waters here, so um, please forgive me. Yeah, there's no, my 2 is missing here, right? Because we look at this, we can tell this is not a balanced equation, right? We need a 2 to get the 4 and 4 here. So that's supposed to be a 2 there, everybody. But our final equation will match, right, what we see here, and then we just need to add up our enthalpies. 74 plus negative 393 plus negative 483, and that gives me a total enthalpy of negative 802.5 kilojoules. And this is my final answer using Hess's law. So we can see, right, we had to do a couple of different things. Flip some signs around, multiply some stuff by some factors. We had to do a lot. Let's look at the other way, standard enthalpies of formation. Standard enthalpies of formation. We're taking our products and minus our reactants. So I'm going to take my CO2, enthalpy of formation here, and in this case, I only got 1 mole of it, so I only need 1 mole. Then I have 2 H2Os. Remember, this is a 2 here. So I got 2 H2s, 2 waters here. So 2 enthalpy of formation of water here, minus our reactants. In this case, I'm going to have 1 CH4, so 1 CH4, and then 2 O2s, 2 O2s. So we can see, right, this is our setup. This is it. Products minus reactants. And the coefficients is telling me how many of those things I need. From here, what do? We just plug in our values. So those values I showed you guys earlier, right, we have values for everything. Okay, so in this case, right, the values for my CO2, it's going to be negative 393. Okay, the value of my H2O is going to be negative 241.8. Okay, which we see here. The value of my CH4 is going to be negative 74.6, which we see here. And I have a value of 0 for O2. Why do I have a value of 0 for O2? Because it's an element, right? In this case, oxygen exists as a O2. Okay, so it's just going to be 0. So this is 0. And then what do we do from here to find our actual enthalpy? Well, we're going to take our products and minus our reactants. That's it. All right. And what I see here, once I multiply this by this other 2 times negative 241 minus our negative 74.6 plus 0. That's going to give me my answer of negative 802.5 kilojoules. The same exact answer what we did from before using Hess's law. Okay. So this is two different ways, everybody. Two different ways, right? Hess's law, you got to add up these equations. But with enthalpy, standard enthalpy of formation, you're doing products minus reactants. And that's it. Okay, so that's why they say this is the most convenient way, because that's very convenient, right? It took me two less than 2 minutes to do this problem. Of course, it took me a little bit longer to do this type of problem, right, with Hess's law. All right, but it's good to know both ways. Okay, so everybody, this is standard enthalpies of formation, and I will see you guys on the next video.